What if 1 hour of your life cost somebody else 7 years of theirs? I mean, that's not just some philosophical riddle. It's the actual scientific puzzle right at the heart of the movie Interstellar. So today, we're diving into the real-world physics behind one of the most mind-bending ideas in movie history.
It sounds like something straight out of a fantasy novel, right? But this is the core question that powers the entire mission to Miller's planet. How is it even possible for time to flow so differently for people in the exact same universe? Well, let's find out.
Okay, so to really get our heads around this, we need to go to the scene of the crime, so to speak. We're heading to a water world that just happens to have a very, very powerful neighbor.
And here we are, Miller's planet. Now, the key thing to understand is that the planet itself isn't the star of the show here. It's what it's orbiting, Gargantua, a monster of a supermassive black hole. Its immense gravity is the engine driving this whole crazy phenomenon.
Now, you might be thinking this is just some clever Hollywood trick, right? But the amazing thing is, this is all rooted in the work of one of the greatest minds in history, Albert Einstein. So let's break down the actual physics that makes this sci-fi idea a reality.
It really all boils down to a fundamental idea from Einstein's theories of relativity. And it's pretty simple. The stronger the gravity you're in, the slower time passes for you compared to someone in weaker gravity. For Miller's planet, this one rule is doing all the heavy lifting.
And this effect isn't subtle. It scales up dramatically. Here on Earth, our gravity is pretty modest, so time for us is only slowed by a few microseconds a day compared to an astronaut in orbit. But then you jump over to something like a neutron star, and that effect is amplified to hours per day. And at the very edge of a black hole, where gravity becomes effectively infinite, well, time grinds to a complete stop. It's like a dial that gravity can turn all the way up to 11.
Okay, so gravity slows down time. We get that. But why? How does that even work? The whole concept can feel a little abstract. So to get a better feel for it, let's try a quick thought experiment. Let's call it the tale of two astronauts and a laser.
So picture this. You have person A who's floating right next to a really massive object, like our black hole Gargantua. And then you have person B, who is way, way out there in deep space, far from any serious gravity. Person A decides to send a quick hello to person B using a simple green laser pointer.
Now, we all know light is a wave, right? It vibrates. And the color green, specifically, corresponds to light vibrating at an absolutely staggering 600 trillion times every single second. So, for every 1 second that ticks by on person A's watch, they send out a beam of light that has 600 trillion little wiggles in it.
But here's the catch. For that laser beam to travel from person A to person B, it has to literally climb out of that deep gravitational well created by the black hole. That climb takes a lot of energy. And for light, losing energy means its frequency, the number of wiggles per second, has to go down. This effect has a name. It's called gravitational redshift.
So by the time that little laser beam reaches person B, it's exhausted. It has lost so much energy that it's no longer vibrating 600 trillion times a second. Let's say it's now vibrating at only 10 billion times per second. It's not even green light anymore. It's been redshifted so much, it's now a low-energy microwave radio beam.
And this leads us to the critical, head-scratching question. Person A knows they sent 600 trillion wiggles in their 1 second. But person B is only receiving 10 billion of those wiggles per second. The wiggles can't just disappear into nowhere. So, where did they go?
The only possible answer, the only way the universe can make the math work, is that time itself is flowing at different rates for each person. A second for person A is a fundamentally different length of time than a second for person B. And that, right there, is gravitational time dilation.
Let's just run the numbers real quick. If person B is only catching 10 billion wiggles per second, it's going to take them 60,000 seconds to receive all 600 trillion wiggles that person A sent out in what he felt was just 1 second. 60,000 seconds, that's nearly a whole day. 1 second for person A equals almost a full day for person B. Mind-blowing.
And here is the most crucial part to understand. This isn't some trick with broken watches or faulty equipment. This warping of time affects everything. We're talking mechanical clocks, digital clocks, and even our own biological clocks. Our heartbeats, our brainwaves, the entire aging process. From person B's perspective, person A would look like they were living life in the most extreme slow motion you could ever imagine.
Okay, now that we have a grip on the science, let's bring it all back to the movie. How well does Interstellar actually hold up? when we put it under the scientific microscope. Let's do a little fact check. First, a really brilliant detail the filmmakers threw in. When the crew is down on Miller's planet, listen really closely to the musical score. There's this constant, prominent ticking sound. Well, get this, each one of those ticks you hear actually represents about 21 hours passing for the poor crew member they left behind on the spaceship. It's just a subtle, powerful way to make you feel the time slipping away.
But that brings us to the million-dollar question. Is a planet like Miller's actually scientifically possible? Could you really have that insane level of time dilation and still have it be a place where human astronauts could survive?
The short answer is not really. See, the movie says the gravity on the planet is 130% of Earth's, but to get that 1 hour equals 7 years effect, the planet would have to be orbiting right on the razor's edge of the black hole's event horizon, the point of no return. And if you were there, the tidal forces from the gravity would be so immense, the astronauts would be instantly crushed by a weight of millions of tons. So, not exactly survivable.
So does that mean the movie failed? Not at all. This is exactly what great science fiction does. It takes a real, fascinating concept from science and pushes it to its absolute extreme in order to tell a powerful, compelling human story.
The reality is, if the filmmakers had been 100% scientifically accurate, there would be no story on Miller's planet. The characters couldn't land, and they certainly couldn't survive. By bending the rules just enough, they transformed a really complex physics concept into one of the most beautiful and emotionally devastating sequences in all of cinema.
And in the end, that's what the film is all about. It's not just about the cold, hard physics. It's about that human drive to push boundaries, to solve puzzles, and to overcome completely impossible odds. It reminds us that when we are faced with the truly mind-bending realities of the universe, our greatest instinct is to believe that we'll find a way. We always have.